Hello everyone, my name is Smith Bhake and the topic for my presentation is Electrochemical Impedance Spectroscopy, which is a powerful tool for material analysis. Following up with the content, we'll be seeing introduction, theory, working principle, data interpretation, application, and its advantages and limitations. So what basically electrochemical impedance spectroscopy is? It is a versatile and widely used analytical technique that provides valuable insights into the electrical and chemical properties of the materials. So basically, if you have a battery and you want to know what is going inside that battery, what kind of chemical reaction or the kinetic it is following, so in that case you need to perform this experiment so that you can know the behavior of the material, and in the later stage you can go on optimizing the performance or design of the material. So by applying a small amplitude alternating current signal to an electrochemical system and measuring the system response, this EIS can allow researchers to study a wide range of materials, from batteries and fuel cells to coatings and corrosion process. So what principle it follows? It follows a concept of impedance, which is a resistance to flow of alternating current in an electrochemical system. So by applying a small AC signal and measuring the system response, researcher can gain insights into the capacitive, resistive, and inductive properties of material under investigation. And frequency dependence, EIS examines the electrochemical system response over a wide range of frequencies, typically from millihertz to megahertz. And this frequency dependent behavior provides information about the various processes occurring within the system, such as charge transfer, mass transfer, and surface reactions. So what is the main advantages of this spectroscopy? That it is a non-destructive technique that allows for the study of complex system without significantly disturbing the system equilibrium. And it provides a wealth of information about the system properties and kinetics of the ongoing electrochemical process. So we know that it works in the principle of impedance. So what actually impedance is? So this involves three components like resistance, capacitance, and inductance. So impedance can only be sometimes resistance, and can only be capacitance, or can only be inductance, or it can be combination of all three components. So let's see what resistance is. So resistance is opposition of the flow of direct current in a DC circuit, and capacitance is the ability of material to store an electric charge, and inductance is a property of circuit that opposes charges in the flow of current. And in EIS inductance, it can be associated with presence of electrochemical reaction involving adsorbed species or electrochemical process occurring at the interface. So what is the basic setup of this EIS system? So it comprises of three components, that is a potential stat, a electrochemical cell, frequency response analyzer. So the potential stat is a central component of the EIS setup, responsible for applying the AC voltage signal and measuring the resultant current response. An electrochemical cell is a cell houses the working. This cell houses a working electrode, which is the material under investigation, and the reference electron and counter electrode, which form the three electrode configuration, as you can see in this picture. So, and what is a frequency response analyzer? It is a this FRA generates a AC voltage signal and measures the system impedance response over a wide range of frequencies. So what is the major step of measurement during the experiment? So first AC voltage signal is applied and the current response is seen, and that frequency sweep is done, and at the last impedance calculation is done. So AC voltage signal, EIS applies a small amplitude sinusoidal voltage signal to the electrochemical system, typically in the range of 5 to 50 millivolt. And current response, the system response is measured as the resulting current, which may be shifted in the phase and have a different amplitude compared to the applied voltage. Frequency sweep, the AC voltage signal is applied over a wide range of frequencies, just we talked earlier, typically from millihertz to megahertz, to probe the different electrochemical process occurring in the system. So it is necessary that you change the range of the frequency so you can disturb the different kind of electrochemical process that are undergoing that material. And at the end, we do the impedance calculation. The impedance of the system is calculated as the ratio of applied voltage to the measured current response, providing insights into the system capacitive, resistive, and inductive behavior. So what is the working principle? So so in EIS experiment, a potentiostat applies a sinusoidal potential, as you can see this in this figure. A sinusoidal voltage or the current is provided to an electrochemical system. This can be an electrochemical cell or anything that is under the investigation. And the resulting current signal is recorded and analyzed. So the resulting is the red one is the resulting response, which will later be recorded and be analyzed for the impedance calculation. So if we applied signal, if the applied signal is potential and the measured signal is current, it is referred as potential static EIS. Okay. So and when the applied signal is current and the measured signal is potential, it is referred to as galvanostatic EIS. For the case of potential static EIS, the equation is given as this, where where ET is a potential as a function of time, and E naught is the initial potential, and omega is the angular frequency, and T is the time. And the user controls the frequency and amplitude of the input potential signal with the potential stat and frequency response analyzer. The measure output signal, current signal, the measure output current signal has the same frequency as that of the input signal, but its phase may be shifted by a finite amount known as phase shift. As you can see in this picture, there is a phase shift of phi. Okay, so the measured output current amplitude will vary with the impedance of the electrochemical system at a given frequency. So we saw the input in equation of input, that is Et is equal to E naught cos omega t, and the output signal, and the equation of the output signal would be in the current, that is it is equal to I naught cos omega t minus phi, where phi is the phase angle. So here in this picture you can see how frequency is varying throughout the time for probe the different electrochemical process that is undergoing into a electrochemical system. And this is a overall calculations of the pictures of the electrochemical system. Now coming to the data interpretation, how the data is interpreted after the response had been analyzed. So the result of plotting the input and output signal on the signal current versus potential graph is called Lissajous plot. Okay, so this plot is which you are seeing is a Lissajous plot. The shape of the current versus potential Lissajous plot is a straight line if the input and output signal are in phase. If the input and output signal are in phase, the graph would be a straight line, and if it is out of phase, the graph would be in an oval shape. That means the output signal is completely out of the phase, plus or plus minus 90 degree with respect to the input signal. So once the potential stat collects the potential versus time and the current versus time data at each frequency, a fast Fourier transform is applied to the data. The FTT, that is fast Fourier transform, converts the potential versus time and current versus time into potential magnitude versus frequency and current magnitude versus frequency. The potential amplitude, current amplitude, the potential amplitude, current amplitude, and the phase angle at each frequency are determined from the FTT analysis. With these data, we can describe the different plotting convection associated with EIS. And this can be seen in this picture, how the fast Fourier transform has been implemented in this graph. The magnitude of the impedance is equal to the potential amplitude divided by the current amplitude. That is, modulus of Z is equal to E naught by I naught. If we plot the magnitude of the impedance and the phase angle as a function of frequency on the double axis plot, we get what is called a body plot. So you can see this is known as the body plot. So in a body plot, magnitude of Z versus F is displayed on the primary vertical axis, this one, and phi versus F is displayed on the secondary vertical axis, this one. So frequency and impedance magnitude are normally plotted on a logarithmic scale, and while the phase angle is displayed linearly. And there is also another way to express EIS data, like we can use polar coordinates. These two pictures shows the polar coordinates of the EIS system. That's plotting Z, modulus of Z as a ray originating from the center at an angle equal to phase angle. and this can be seen as this equation, that is the z modulus of z is equal to under root of z square zy square. So the impedance associated with the x-axis is referred to as real impedance ZR. This is referred to as real impedance, and the impedance associated with the y-axis is referred to as imaginary impedance, that is ZI. And the negative imaginary impedance, and this is a negative imaginary impedance on the y-axis, we get a Nyquist plot. So this is known as a Nyquist plot. So Nyquist plot are the most common form of displaying impedance data, followed by Bode plot. Bode plots allow easily determination of frequency values compared with the Nyquist plot, where frequency values are not plotted. Generally, the lower leftmost points on the Nyquist plot correspond to the highest frequencies, and following the trees of the right moves from the high to low frequency. As you can see here, the lowermost point. This is the lowermost point. This denotes a highest frequency. Sorry. So this denotes a higher frequency, and this followed by traces of path. This is the low frequencies. In total, an electrochemical impedance spectroscopy experiment results in 5 columns of data, that is F, that is frequency, ZR, that is the real impedance, ZI, which is imaginary impedance, and phi is a phase angle, and modulus of Z is a resultant impedance. So after getting the plot data interpretation, we go on circuit modeling. So there is a circuit that is mostly followed, that is a Randall circuit. A Randall circuit is a common equivalent circuit model used to represent the behavior of an electrochemical system. It consists of solution resistance, that is denoted by Rs, a charge transfer resistance, that is RCT, and a double layer capacitance, that is CTL. And there can be some additional element also, like depending on the system under investigation, other circuits elements such as Warburg impedance, that is ZW, for the mass transfer process, or inductive elements L may be included in the equivalent circuit model. So and for the constant phase element, like in a more complex system, a constant phase element CPE is often used instead of an ideal capacitor to account for non-ideal capacitive behavior, such as surface roughness or inhomogeneities in the material. And at the last, the data is fitted to the experiment data is fitted and is analyzed. The researcher can extract quantitative information about the physical and chemical properties of the system, such as reaction kinetics, diffusion processes, and interfacial characteristics through these data. So here the example of some circuit modeling. Like for a pure resistor, the modeling is given like this, just a straight line along the x-axis. And for pure capacitance, it is a dotted line along the y-axis, negative Z. And for example, you can see here, and here, for a R and C in series, if the resistance and capacitance are in series, the graph can be plotted as this. And if the resistance and capacitance in parallel, this can be plotted as this. So if we take an example, if the plot is showing something, if the Nyquist plot is showing this kind of graph, so we'll be getting this kind of circuit. This is our model circuit. So this is basically a circuit of a lithium battery cell. So this is generally what you will get if you analyze the lithium battery cell. So here are some common example of Nyquist plot. Like it can be semicircle, two semicircle, and Warburg diffusion. This line denotes the Warburg diffusion, that is for mass transfer. Now coming to the application of EIS, it is generally used in corrosion, batteries, fuel cell, and many more. So corrosion monitoring, EIS is widely used in study of corrosion behavior of metals and coatings, providing information about the formation and degradation of protective films, as well as the kinetic of corrosion process. And before only I explain about the battery and the fuel cell. So it is a valuable tool for studying the performance and degradation mechanism in energy storage devices such as batteries and fuel cells, enabling the optimization of their design and operation. Also used for coatings and thin films. It is used to characterize the protective properties, adhesion, and degradation of various coatings and thin films, including paints, ceramics, polymers, which are essential in many industrial applications. Electrochemical sensors And also using electrochemical sensor is employed to study the performance and sensitivity of the electrochemical sensors such as pH sensor, gas sensor, and biosensor by providing information about the electrolyte interface charge transfer process. So at the last, we'll be seeing advantages and limitations. So what are the advantages? It is a non-destructive analysis, provide detailed information on electrochemical process, versatile technique applicable to wide range of material and system, and allows for study of complex system with multiple components, enables the extraction of quantitative parameters through modeling. And what are the limitations? It requires a careful experiment design and data interpretation, relatively complex data analysis and equivalent circuit modeling. It is sensitive to experimental conditions such as temperature and humidity, possible interference from plastics, effects on the non-ideal system behavior, and limited spatial resolution for the surface or interfacial characterization. So that was it for presentation. Thank you.